I hope I can be in person with all of you sometime in the not infinite future. I've got a 4-year-old at home, and I'm feeling very conservative about moving myself around, but hopefully that's going to end soon. Anyway, I want to tell you predominantly about the theses of two of my students who are finishing up this year and who are both spectacular, Scott Carlston and Erin Kato Fong. In the case of Erin, you will get an in-person talk from her soon, I think in the next month. And so it's just going to be an advertisement. She is far better at talking about her work than I am in any case, so I'm excited about that. Sarah, are you going to be monitoring for hand raised and such?
Yes, I can do that.
Awesome. And those of you who know Princeton know that we're big believers in interrupting. So please feel free to stop me. There's some people.
Yeah, so it seems like someone's still in room 940, and maybe can they just log off? I'll go tell them to log off.
Okay. So just to make sure we're all in the same mental headspace, I like to take this convention from James Bullock and Mike Boylan-Colchin's 2017 review. What do I mean by dwarfs? And astronomers, of course, love arbitrary subgroupings of objects. So in terms of dwarfs, we often think about bright dwarfs that are sort of LMC, SMC kind of mass. And then the classical dwarfs that I learned about in graduate school, extending down to about 10 to the 5 solar masses. And then the ultra faints. I will not be talking about ultra faint dwarfs today at all. I'll really be focusing on populations of galaxies outside the local group. And when I talk about Scott's work, it'll mainly be in this classical dwarf regime, and then Erin is mainly focused on brighter dwarfs. So the basic context, of course, is that we have now a very good idea of our cosmological model, and a lot of the exciting prospects for understanding cold dark matter come on small scales, and we can make predictions for the shape of dark matter halos and subhalos, the mass function of subhalos, and the distribution of subhalos within larger halos, all of which hopefully will lead us to understand whether our cold dark matter model works. And for a lot of reasons, we hope that a fruitful line of inquiry will indeed be to look at dwarf galaxies. One reason is that they are some of the most dark matter dominated structures in the universe. This is just dynamical mass here on the x-axis and mass to light ratio on the y-axis. And so you can see that dwarfs and galaxy clusters here at high mass are among the most dark matter dominated structures. Therefore, we might hope that all of the baryonic physics that we don't understand completely is less important in this regime, and we can actually study more pristine dark matter halo shapes, for instance. But there are obviously many complications. So for just a brief overview of some of these potential challenges, the first thing you, of course, want to do is count low mass halos. And for a long time, we've talked about whether or not there are enough of these low mass satellites. Another way of posing this problem is how do we properly put baryons into dark matter halos, particularly as we go to low masses. We are also do not find agreement between the predicted shapes of dark matter halos and the observed rotation curves. So the velocities rise more slowly than would be predicted from generic cold dark matter models, potentially suggesting that we have our dark matter model wrong. There's also been a suggestion that satellites may not be distributed uniformly in bigger halos, but may be found in planes. Again, not a prediction of standard simulations. Maybe could be explained because satellites come in groups. These are some of the small scale challenges that people have talked about. And there's this tantalizing possibility on the one hand that they're going to lead to breakthroughs in our understanding of the nature of dark matter. On the other hand, there are all of these baryonic effects, the importance of reionization, particularly for these very low mass subhalos, the role of stellar feedback, which we know happens because we see supernovae driving winds, we see vigorous winds coming out of dwarf galaxies, and then environmental effects like tidal effects when subhalos fall into bigger halos, ram pressure stripping if there's enough hot gas that the galaxies are moving through. And so we have to simultaneously understand the baryonic effects if we really want to use any tracer, even dark matter dominated dwarfs, in order to get at the dark matter models. And so Scott and Aaron's theses are both tackling both sides of this question. And Scott in particular wanted to build a sample of satellites around Milky Way mass halos to get us away from somewhat perhaps over-tuning our simulations to reproduce the satellite mass functions for the Milky Way and Andromeda, which they are indeed now able to do. So this is just one example from Garrison Kimmel. You can see the Milky Way is the solid, Andromeda is the dashed, and the models are all of these colored lines. And so the question is, can we build larger samples in order to figure out which of these challenges really are challenges and which baryonic effects are important in solving them? And really the insight that Scott had is that with the same imaging data in many cases that you use to find satellites of Milky Way mass halos, at least within the local volume, so out to about 10 megaparsecs, you can also derive adequate distances from surface brightness fluctuations to figure out whether those faint fuzzy things are associated with a given halo, and thus very cheaply put together large samples of satellites, really with imaging data alone. And this was the basis of his thesis work, exploration of local volume satellites. So just to emphasize why, of course, in astronomy, distances are always a challenge, but just to bring it home, let's look at M101. So M101 is this Milky Way analog. It's 7 megaparsecs away. Its circular velocity is 210 kilometers per second. And it's a natural candidate to look and see if we can characterize its satellite population. So Bennett and Dave Sand and collaborators in 2017 published this list of potential candidates, all the red stars. And there were others like Alison Merritt and others who published potential friends of M101 in the colored symbols. But let's just look at the red stars. There's 43 of them. That's a lot of satellites, way more than the Milky Way at the sorts of masses that they're sensitive to here, down to a few times 10 to the 5. And you can't help but notice that most of them are on one side of M101 and close to NGC 5485, which is a background group. So in order to figure out which of these really are friends of M101, you really need distance. How can you do this? Well, classically, you could get HST imaging for each satellite and use distances like tip of the red giant branch. That's expensive. This is what Shani Danieli has done for a few potential friends identified with Dragonfly. You could do the trick that Marla Jiha and Risa Wexler and others are doing and get radial velocities for every goddamn thing. And this is very, very expensive as well. So this is what the Saga survey's been doing. Or you could do statistical corrections, and that can be interesting, but also limits the kinds of science that you can do. And so again, the insight that Scott had was that he could use surface brightness fluctuations, which I'll describe in the next slide. And he was able to show from the same CFHT data that Bennett used to select that candidate list, he was able to show that only 2 of them, these blue octagons here, are in fact associated with M101. All the rest are background, and many are likely in this 5485 group. So how did this surface brightness fluctuations thing work? Well, the idea is seems kind of like magic. At least I felt that way when I first came to understand this technique. But the basic idea is, of course, if you take the same galaxy and you put it further away, the surface brightness will be preserved. But because the light that we see from galaxies is dominated by the very brightest stars, the number of stars in a given pixel is going to go down with distance, and therefore the Poisson fluctuations per pixel will go down with distance. And so if you can measure, and you can see in the bottom panel here, this is the SBF, this is actual variations, pixel to pixel, in the RMS around the mean number of stars. And the power in those fluctuations scales with the distance. That is how surface brightness fluctuations work. Now, of course, the fluctuations also scale with how many luminous stars you have, and that is a function of the stellar population. And so typically, SBF is calibrated to a single optical color, and you can do extremely well, very precise distances for elliptical galaxies. This is shown for SBF from the ground, from Cantiello, using Virgo and Coma to calibrate the distances. What Scott has done is extend the SBF calibration to much bluer colors, where there's really quite a bit of scatter, because the assumption that, or it's clearly not true, that star formation completely ceased in these galaxies a long time ago. And so exactly the star formation history of the galaxy contributes to scatter at a given color. And you can see a recent paper by Johnny Greco that looks at this in detail. But we got a sample of galaxies where we have both TRGB distances and SBF, and directly calibrated the SBF distances as a function of G minus I color. And we found that we could measure distances good to 15%. So nowhere near as precise as what you can get for a massive red galaxy, but good enough to determine whether or not a satellite is in a host halo or in the background. So that's the game that we're playing with ELVES. We can get with CFHT or Gemini ground-based imaging, we can get out to about 10 megaparsecs. This is a volume-limited sample of hosts in ELVES. In color are things that have red stars, or things that Scott published in 2020. There's obviously a bunch of hosts that have already been done in the literature, and then he's finishing up the full survey paper, which will be roughly 30 hosts altogether. So that's the sample. He's characterized his completeness in terms of both selection and our ability to measure SBF, and we can roughly get to a few times 10 to the 5 solar masses. There are a handful of galaxies that are either too diffuse, so lower in surface brightness than 26.5 magnitudes per square arc second, or too small, that we're still, this mass limit is a little bit of a fuzzy boundary, but roughly speaking, we're complete to there. So here are the first luminosity functions that Scott published from that first paper in 2020, just divided into things that likely have halo masses like the Milky Way, and those that are likely in small groups, so M81 groups, Cene, etc., Sombrero. And so there's lots of, I sort of really enjoyed staring at these luminosity functions when we first were putting them together. You can see there's some gaps. What we decided to do in order to compare with models is take the dark matter halo trees, not the hydro, from illustrious TNG 100, which has high enough spatial resolution that we can get down to the halo masses that we need to describe Scott's sample, and then just use abundance matching on top to compare between the satellite properties in TNG and those in our observations. He also compared with Nihao and Fat ELVES, but I'll mostly focus on the TNG comparisons here. So the first thing we looked at was just the richness. And there seems to be decent agreement between the scatter in the number of satellites that you would predict, which is shown in the grayscale here from Illustris using the Garrison-Kimmel abundance matching, and what we observe, which is all of these red points. And so overall, the number of satellites per host seems consistent. We talked briefly about an excess of bright satellites at the LMC luminosities and compared to the theory, but that really gets into the details of how you do the abundance matching, and I don't think is robust enough to discuss now. One thing that we spent a long time staring at and still don't understand is that while the total number of satellites seems to agree with predictions, their radial distribution seems to be more concentrated than what you would expect. So again, grayscale here is the expected half light, half size radius for where half of your satellites should be, and this is the distribution of observed sizes for the satellite distribution. So in any given case, we're 1 to 2 sigma away from the mean expectation, but we systematically are seeing more centrally concentrated satellite populations. So maybe this is interesting. Saga, who've now published 30-something hosts and have the data now for, I think, almost all of their 100 hosts, are not seeing this. And whether that's in detail because their hosts tend to be lower mass, we have some of these bigger ones, or whether we're just unlucky here in the local volume, I don't know yet, but this is sort of an interesting trend that we'll see if it holds up in Scott's full sample. Another really cool thing that Saga found was that unlike the Milky Way, most of the satellites in Saga's stellar mass limit is something like 10 to the 6, I think, so a little bit higher than ours. But almost all the satellites that they looked at are star forming. They have spectra, right, because they're using radial velocities to find the satellites, and so they see H alpha in most of their satellites. And we only have colors, right, because we're doing this cheaply with imaging. Our color distribution is much more, we see many more red things, much more like what you would expect from the Milky Way, even if we apply Saga's mass cut. On the other hand, again, we have some of these poor group hosts, so it's not clear whether the mismatch with Saga is just because of the host halo mass. Again, will be really interesting to get a little bit better statistics there on this. Yes.
Do you think the star formation properties and the concentration in the radial distance in the halo, do you think there's any relationship there? Like if you, for whatever reason, happen to have, less star forming objects, would you expect them to be more closer to the centers of the halo? Like, are those like differences correlated, like expected to correlate with one another?
Not obvious to me that they would. I mean, the quenching thing, one still wonders a little bit whether there's a slight surface brightness incompleteness in the Saga sample. But I don't, and on our side, of course, we only have colors. So lots of things that look reddish could well be doing low-level star formation. So I just, we're really not doing a fair comparison yet. But I don't think, even if it were incompleteness, surface brightness incompleteness on the Saga side, it's not totally obvious to me that the puffiest things would be the closest in, although maybe that's true.
Okay.
I have to think about it.
Yeah, I was more just thinking like if you happen to have a sample, even if it wasn't an error, it's just you happen to have a sample which was more central in their halos, they would be, there would be more quenched galaxies. Maybe. I don't know.
Yeah. Yeah, I mean, depending on whether it's just the simulation's getting dynamical friction wrong or not.
Oh, I see. Yeah, okay.
Yeah. That's certainly, I think, on the table for the radial distribution issue. All right, so there are two other papers that Scott recently posted to arXiv that I will not talk about in detail. I'm just going to give you at least one top level thing from each paper, but each could be its own talk for sure. So he has looked at the structures of the ELVES satellites and the kind of, at least to me, surprising punchline is that the red and the blue satellites have exactly the same mass size relation. Again, this is below 10 to the 8, so 10 to the 5 to 10 to the 8. He does not see a difference in sizes. He sees a small difference in intrinsic shape in the sense that the red things are rounder than the blue things, but no difference in size. So that's a kind of interesting punchline. I don't think he's the only person to see that, but it is a quite nice complete sample down to 10 to the 5. He also looked at globular clusters and nuclear star clusters being similar in size to globulars, a few to 10 parsecs in size, but more massive, and obviously found at the centers of their galaxies, thus nuclei. And the fun result here is a very clear trend with host halo mass or something to do with environment, such that the fraction of satellite galaxies that harbor nuclei at fixed mass rises as you go to denser environments. So coma, so at 10 to the 7.5, if you're a satellite in coma, you have twice the likelihood to host a nucleus as if you were a local volume satellite. And this is echoed in the number of globular clusters as a function of host environment. And clearly those two are related, since we think, at least in this mass range, that globular cluster mergers likely were the source of the nucleus early on. And so that's an interesting result that I don't fully understand which aspect of environment matters, whether it's sort of that you were more vigorously star forming if you fell into a cluster early, and so you're more likely to have a lot of globulars and thus a nucleus, or something else. But that's a fun result to look out for later.
What was that? I've not heard a study of the globular frequency versus environment before.
Well,
Is this a new thing, or?
Peng sees this as a function of radius in Virgo. So there's been some discussion of it before.
Ah, okay.
And we see the nucleation fraction as a function of radius in the local volume satellites even. That's what the right-hand plot is. The samples in Virgo are kind of complicated because they don't go very far out. And so I'm still a little bit fuzzy on how well we understand the environmental dependence for the globulars. But I don't think we're the only people to see that.
Oh, that's cool.
Yeah. All right. That is all I'm going to say about Scott's thesis. I would like to spend a bit of time really focused on questions of stellar feedback and other baryonic effects that might impact dwarf evolution. And this is really coming to Erin Cadeau-Fong's thesis. She's been focused on using this sort of exquisitely deep and high spatial resolution imaging from the Hyper Suprime Camera Survey, but still, and she's quite interested in dwarf galaxy evolution, but still limited to spectroscopic samples of dwarfs from SDSS and gamma. And Mike and others on this call know how hard it is to put together complete samples in this low mass regime. And so that's still something that we're struggling with. But the first thing Aaron did, which I won't talk about at all, was select samples of dwarf mergers by looking for tidal features and show quite convincingly that recent merging activity boosts star formation rates in these dwarfs. What I'll talk about today is her work looking at the intrinsic shapes of dwarf galaxies, which is really enabled by the fact that we can get out to 4 RE given the incredible surface brightness sensitivity of the HSC imaging. And so the idea is that, of course, we see projected images of galaxies on the sky, not their three-dimensional shape, but we can get at an average shape if we look at the distribution of projected shapes on the sky. So you can imagine if your galaxy is very flattened like a dinner plate, that when you see it face on, it will look round. When you see it edge on, it will look flat. And so for disky things, you really expect this very broad distribution of projected B over A. If you're spherical, you're going to look spherical no matter what. And if you're prolate, you will most often look elongated, but occasionally you'll be seen down the short end and look round. And so with these distributions, you guys still see my slides?
Yes, the next slide seemed blank. Now we do, yes.
Okay, sorry, something paused. I don't know, maybe whatever. Anyway, we can invert these projected observed B over A distributions to intrinsic axis ratio space. Okay, so we'll plot things in C over A versus B over A. Here is where disks would live in, a perfect disk would live given errors in the observations. Here's the spheres, and here are the prolates. Okay, so the first result of Aaron's work is that as you go to large radius, you see ubiquitous round, what we call stellar halos. This is not unexpected because it's been seen for many local group and local volume dwarfs in resolved stars, but Aaron sees it in for many thousands of dwarfs. And so you can just see that the C over A distribution gets rounder as you go out towards 4RE. And she's just completed a study using Fire 2 simulations and dwarf galaxies in halo masses of around 10 to the 11 to try and ask where do these stars come from, because we do not expect that enough stars are brought in to dwarf galaxies via merging to build stellar halos in dwarfs the way that we build them in Milky Way mass halos. And indeed, what she found in the simulations is that most of the stars are formed in the disk and then dynamically heated to form that stellar halo. This is also in keeping with the fact that the stellar halos in dwarfs almost ubiquitously show intermediate age stellar populations for the local volume dwarfs that have been looked at. She also found that as you go to lower masses, the galaxies get puffier. Again, she's not the only person to see this, but sees it very clearly. And if you divide the higher mass sample into blue and red, she also finds that the red galaxies are rounder, while the blue ones are these thickened disks. And finally, a sort of fun side project was to ask about the intrinsic shapes of these low surface brightness galaxies that are also being found in large numbers thanks to recent deep imaging surveys, including Johnny Greco using HSC, but also Teneglidis with DES, and also a Luke Leisman sample that was selected with H1. And so in all of those cases, to the best of our ability to match in mass, we find that the low surface brightness galaxies are puffier than the high surface brightness dwarfs, almost as if we see the stellar halo only and no disk. And that's true even for the gas rich ones. So that's a sort of interesting result. It's true for the ultra diffuse galaxies in rich environments, but it's also true for blue star forming super low surface brightness galaxies. I'm not sure what that tells us as far as what's the most likely formation path for these super low surface brightness galaxies, but it is quite interesting. So just to conclude the dwarf galaxy part of my talk, from Scott's ELVES survey. This is a survey of classical satellites around Milky Way hosts in the local volume. We're finding that the richness of the satellite population seems to agree with simulations. The radial distribution seemed to be more concentrated than you would expect. And we find lower nucleation fractions in local volume than in denser environments. Aaron has showed very clearly with large statistics that dwarf galaxies are rounder in their outer parts. And we think that those round stellar halos are built from in situ stars being dynamically heated. It's also true, I didn't mention this, but most of the fire dwarfs actually do not form a proper disk and instead are very, very triaxial. And so another sort of important punchline of Aaron's thesis is that these measurements of intrinsic shapes provide rather stringent tests for hydrodynamic cosmological simulations in terms of whether they can describe the shapes of dwarf galaxies. Next step for Aaron's science is really to have much larger, more complete samples, at least down to 10 to the 8. And she's working with Alexei Leothod and some of our collaborators, Shani and Song Wong, on this Marian survey, which is a large survey with the Blanco telescope to get 2 medium bands, one around where H alpha will be at a redshift of 0.05 to 0.1 and the other at 0.3. And this is to get better photometric redshifts for dwarfs in that redshift range down to about 10 to the 8. Alexei, of course, wants to do weak lensing for these dwarfs, so we're looking for 100,000 dwarfs, but it will be all overlapping with HSC, and it will be a spectacular sample to study dwarf structure, dwarf shapes, and we'll have H alpha imaging, and so we can look at the relationship between all of those things and the star formation as well. So keep an eye out for that. I can pause here and take questions. I do have a black hole part of the talk, but we're also, you tell me whether I should keep going or pause.
I did have one question, which might lead to other people thinking too. So I was wondering, for Aaron's work, there should be some accretion around these dwarfs, right? Is that something you can kind of rule out with your data? And does fire really resolve down to low enough stellar mass accreted halos that you would really see this if it did occur?
So clearly dwarfs in this mass range do merge with other dwarfs. She picked out that sample of dwarf mergers. At least my understanding of the, Rachel says black holes, of the argument is that because the stellar to halo mass relation is steep, even though you may be accreting dark matter halos, you won't be bringing in that many stars. And so, yes, she sees, I mean, there's not that many fire simulations, but yes, she sees some stars that come in that are ex situ. You saw the fractions are not 0, but they're much, much lower than a Milky Way mass system.
Yeah, thank you. And I think no one else raised their hand, so you're good to continue.
All right, so my longstanding question about dwarfs has really been, how often do they harbor black holes at their centers? I don't know about you, but I'm really waiting and terrified for when the decadal survey comes out. But I believe the next decade is going to be the decade of the black hole. There's so much exciting prospect for high spatial resolution data that in particular is going to break open this question of whether or not there are intermediate mass black holes. So of course, we're learning a stunning amount about the demographics of stellar mass black holes, extending all the way up to 100 solar masses on the one hand. Astronomy just got a Nobel Prize, Andrea Ghez and Reinhard Genzel, for their exquisite measurement of the black hole at the center of our own galaxy at 1 million suns. But there is a complete dearth of understanding as to the mass function and even the existence of any black holes in between those two mass ranges. And it is not idle curiosity that leads us to wonder whether black holes live there. It is really the fact that we do not believe that supermassive black holes can appear at 1 million or 1 billion suns from the ether. We think they have to grow from seeds, and therefore there should be some relics of that seeding process that we can find in the universe today and at higher redshift. And their mass distributions, how they occupy galaxies, how they occupy the halos of galaxies, should tell us something about those seeding processes. People think about 3 main avenues for making seed black holes. The first is the same way that we make stellar mass black holes, through the death of massive stars. But the thought is that at very early times, very low metallicities, your first generation of stars would be massive enough that they could make 100 solar mass black holes when they die. These POP3 remnants then would be a little bit closer to the 1 billion suns that we're trying to grow by a few 100 million years after the Big Bang. That path, however, seems very challenging. It's really hard to force that much material into a black hole that quickly, because of course, when black holes accrete, they emit light, and that makes it very hard to grow them that fast. And for that reason, people have developed these direct collapse models where you don't have to form a full star that fuses and lives its whole life. Rather, you have very low angular momentum gas that forms somewhat directly a 10 to the 4, 10 to the 5 solar mass black hole. And for this to work, as you can imagine, you need not only for the gas to be in the very low angular momentum tail so that it can collapse, you also need to make sure it's exactly the right temperature so that it doesn't fragment into smaller clumps, but that it's not too hot so that it can actually coalesce. And so, people put their gas clouds at exactly the right distance from other star forming regions. So there's some UV photons to keep the gas where it needs to be. This is a pretty rare occurrence. It may be able to explain the first quasars that we see. It seems to me unlikely that all supermassive black holes were seeded through this direct collapse channel. I think the number densities that people are predicting are just way too low. But that would make you a heavy seed, 10 to the 4 to 10 to the 5. And then the final pathway that we talk about is gravitational runaway in the centers of dense clusters. And this can either happen quickly. If you have a very dense star cluster, you can basically have stars that merge in the center of the cluster and then form a very massive black hole. Or you can have a slow channel where you have multiple black hole mergers happening dynamically as the cluster evolves, eventually forming an intermediate mass black hole. And these channels also have challenges. If you want to have multiple black hole mergers, you expect you're spinning the black hole up, and you need the gravitational potential of this star cluster to hold onto the black hole and not let it fly away. So that's hard. The one exciting thing about this channel in particular is that it could happen at all cosmic time rather than only early when gas was pristine. And if it's gravitational runaway, then you do expect to have a bunch of black holes outside of galaxy centers. So that is a testable prediction that sort of sets this channel apart from the other two. And so the hope is that if we can gather demographics on black holes locally, that we might be able to gain some insight into which of these seeding mechanisms operates. So observationally,
there's a question.
Yeah.
From Hog.
Sorry, trying trouble with my mute. It's when you say there would be outside the center black holes, meaning there would be black holes distributed like the stars, or are the predictions more detailed than that? Or am I off?
Well, in that case, it would be black holes in star clusters.
Right. Good.
So, yeah. Either way, no matter what you do, I think you expect some number of black holes outside of galaxy centers, because if a satellite falls into the Milky Way with a black hole in it, then not all of those are going to get there to the center by dynamical friction in a Hubble time.
Yeah, exactly. Yeah, I mean, it's to me, I mean, this is a broken record for me, but it seems surprising to me how well centered all the black holes are, and whether that's a problem for all these different kind of pictures.
It is just that we don't know how to look for them if they're not at the center, because they don't fuel.
Mm-hmm.
So, I mean, for me, the most exciting thing that I want to do in the next, hopefully less than 10 years, is find more black holes outside of galaxy centers. Tidal disruption events are going to do this. Certainly, LISA will do this. But I think, you know, we were trying to do this with in the Milky Way, and higher spatial resolution will allow us to do it dynamically in many, many more star clusters, right?
Yeah, no, there's a lot of promise, but it's a hard thing to do, to see them purely dynamically.
Yeah. So it's a hard thing to do, to see them purely like dynamically at 10 to the 5 in the center of a galaxy, which is what I'll say next.
Exactly, yeah. But it's even harder if they're not. Yeah.
And
good.
it's even harder if they're not. That's right.
Yeah.
So M33, Carl Gebhardt published an upper limit of 1,000 solar masses from dynamics from the nuclear star cluster as I was starting my thesis. And people concluded, therefore, that low mass galaxies just don't harbor black holes, only massive galaxies. But there was always a fly in the ointment there, because NGC 4395, which is 4 megaparsecs away and kind of a clone of M33, clearly has a very active AGN. So it's got to be more than 10 to the 4 solar masses, and it's probably a 10 to the 5 solar mass black hole. So the question is, can we do better than these two galaxies? That's been the last 20 years of my life, and Anil Seth and Nadine Neumeier, I think, have answered it dynamically. So this is now every low mass stellar thing within a little less than 10 megaparsecs for which someone has attempted to detect a black hole dynamically. So in the case of the globular clusters, the top of these bars are published detections. The bottom are published upper limits. So I think that tells you everything you need to know about the state of that field. It is completely, there are no convincing cases of black holes at the centers of globular clusters to date. There are, however, 5 dynamical detections of massive black holes of around 10 to the 5 to 10 to the 6 in the center of these sort of LMC to less than 10 to the 10 solar mass galaxies, NGC 205, 4395, and these others. And so just very, very crudely, the fraction within 5 megaparsecs is 4 detections out of 8 attempts. And so roughly speaking, 50% of galaxies in this, you know, massive dwarf range host black holes of 10 to the 4 to 10 to the 5. I guess we could have inferred that from M33 and 4395. These statistics are not overwhelming, but it's a tremendous amount of work that people have done fighting against spatial resolution to get these measurements. Just to emphasize here why the globular clusters are so hard. This is G1, which is a massive globular cluster in Andromeda. The papers from Carl Gebhardt and collaborators claim a 20,000 solar mass black hole, really based entirely on this point. Here's what you could do with a TMT in red. And of course, we're in this regime where clusters of stellar mass black holes are very hard to distinguish from one 20,000 solar mass single massive black hole. And so for all of these reasons, as Hogg already said, this is going to be a very hard problem, but much higher spatial resolution will help a lot. So that's pretty much everything we can learn so far from dynamics given present constraints. The other thing that the game that I've been playing for years and years is to look for accreting massive black holes. And here we're up against this similar challenge that a 10 to the 5 solar mass black hole can have the same or less luminosity output than a single X-ray binary, a single supernova, a little bit of star formation. And so it's very hard to robustly figure out whether you're seeing black hole accretion in this regime. And I think the best work, the cleanest work has been done in the X-ray. This is Brendan Miller and Elena Gallo's EMUSE survey. And after correcting for low mass X-ray binaries with the Chandra PSF, it's roughly for stellar masses between 10 to the 9 and 10 to the 10, it's roughly 20% of the galaxies that host accreting black holes. And I think that number is pretty robust. It's been seen by a number of archival searches as well. And that, of course, is a lower limit. And mentioned tidal disruptions. I guess you guys had short at some point. So this is a really bold attempt to use the TDE luminosity function. There's lots of things going on in this paper, but he makes the point that given the TDEs that they see in galaxies below 10 to the 10, the occupation fraction, the fraction of galaxies hosting black holes, needs to be really pretty flat down to few times 10 to the 9 to just explain the tidal disruptions that are seen. And so I'm really hopeful that TDEs are going to be a powerful way of getting at the occupation fraction in the future, although there's a lot of things that we do not yet understand about the rates and the demographics of TDEs too. So we'll need many more systems.
Looks like Hogg has another question.
Sure.
Remind me, I'm sorry to even ask this because it shows that I'm not paying attention to the literature, but what happened to the intermediate mass black hole stuff that looked promising in the early 2000s? Is that over, or does it seem like there are these lower mass black holes, and is that relevant at all to your story?
Which intermediate mass black holes? The stuff that I was doing with Sloan and
people were talking about things that weren't at galactic centers that looked like they were accreting and they would have Eddington ratio.
Oh, ULXs.
Yeah, fine. Yes. That thing.
Yes, so those things are mostly neutron stars. And it was New Star that kind of showed that. So a lot of they're just super, super Eddington neutron stars.
Brutal.
This is the last one standing though. This is HLX1. It is very luminous, 10 to the 42 when it's on in the X-ray. And it does these state changes like an X-ray binary. So it actually really looks like it does not have a surface and like it's a black hole. It lives in a star cluster. It seems like it was a satellite that's mostly been disrupted. So it is an off nuclear, black hole. That's our best.
And it's co-spatial with a star cluster?
That's right. Mm-hmm.
So it's the determination is secure that it is part of this galaxy.
That's right. Yeah, we know it's redshift. We see the star cluster in HST. It's not far away. It's like 30 megaparsecs away.
Okay, good.
And we have some guess that it's a 10 to the 4 solar mass black hole. It's also pretty much the only one in its class. Despite XMM and Chandra having very large footprints now, it's the only one known. Now, it's probably a tidal capture of a star that's orbiting that black hole that's donating the accreted material, right? Because again, it's living out in the halo of this galaxy, so it wouldn't be eating otherwise. So I think arguably such events would be very rare. Nevertheless, it's kind of troubling that we only know of one of them. Something else that we would like to solve. Maybe.
Okay, good, thanks. That answers my question completely.
Yeah, so here's where we are, state of play. So LIGO has gotten us to 100 and is creeping upward. Advanced LIGO will move that mass sensitivity upward. And HLX1 and a couple of things that are not as secure living in this 10 to the 4 regime. Then I've argued that at 10 to the 5, some combination of dynamics and accretion gives us a pretty secure understanding that a large fraction of galaxies are still harboring black holes there. And so you see there's still no information at 1,000 or really hardly any at 10 to the 4. So that's where we are. I will I'll skip the occupation fraction stuff. The last thing we did in this annual review is combine my best guess for the occupation fraction with scaling relations between black holes and galaxies to, I would say this is our best extrapolated guess of the mass density of black holes between 10 to the 4 and 10 to the 5. And you can see it's more than a factor of 5 uncertainty just because of the, just to have a range of occupation fractions that are consistent with the data. We haven't really measured that very well yet. But these sorts of things are important for making predictions for LISA and extreme mass ratio in spirals and things like that. So with that, I will put up this slide about all the awesome ways we're going to unlock this IMBH question in the next decade, and I can take questions.
Thank you very much, Jenny, for a very interesting talk. I'll see if anyone raises their hands. Otherwise, I have a question. Okay, Rachel, you go first.
Thanks, Sarah, and thanks, Jenny. Great talk. Sorry, can you hear me?
I hear you.
Great. Going back to the first part of your talk, were those dark matter only versions of illustrious TMG that you were comparing your dwarf galaxy distributions to?
Yeah.
Or did the okay
the dark matter only? So
they were dark matter only.
Resolution. Yeah, but he also, like I said, he compared with Fat ELVES and Fat and Nihao as well. And all of that stuff was pretty robust too.
Right.
Simulation. Yeah.
Right. No, the question I have, so as you know, of course, if you added in baryons, you would expect galaxies that have orbits that take them near the center to be preferentially tidally destroyed. So I believe Garrison Kimmel showed that you would actually expect to have a larger radius for the satellite distribution if you took that effect into account. And that goes the wrong direction.
The wrong way, yes.
To reconcile your result. But what I was wondering is whether, of course, it will also depend on the concentration of the halo, and you have a small number of halos. So I was wondering whether the scatter that you expect from the scatter and concentration can, sort of encompass that range that you're seeing versus Saga, and whether you've looked at that.
Well, the challenge that we have in comparing with Saga is that we have this volume limited sample, right? So for instance, we have the M81 group, we have the Leo 1 group, we extend to relatively high halo mass, and they have taken this narrow slice in stellar mass, and just because of the way mass functions work, that means most of their halos are on the low mass end of the range for the Milky Way. I don't know if that matters as far as what of the radial distributions, but that is the difference between the two samples, and we would have to be clever about reweighting in order to compare directly with Saga, I think.
Yeah. Yeah, I wonder if you can try to make similar cuts on a simulation.
We also thought about, Annika was on the paper, so we thought about things like, should we be selecting only things that Illustrious thinks end up as spirals? Like maybe there's some, this I think comes back to your halo shaped question, or when most of the assembly happened. And I guess it's possible. When we have 30 hosts, maybe we can play that game.
Great, yeah, thank you.
Cool, and I had a question tying back a little bit to the dwarf mergers again. So I remember a study from Muse data showing that dwarf mergers might not actually funnel a lot of gas to the centers, but instead cause these kind of compressed clusters of star formation. So I was just wondering if that's anything you've thought about in terms of the AGN predictions for dwarf galaxies, if there's not this gas funneling through mergers, and if you think that would actually have a substantial effect, or is that not really dominating what you would see?
So I don't think you need a merger to trigger an AGN in a dwarf. But I couldn't, 30 years of battles in the AGN community about whether you need mergers to trigger AGN. We certainly don't have the statistic to play that game in the dwarf sample in particular. I can say that overall, we don't see we don't see differences in color between the AGN and the non-AGN particularly, and we don't see them to live in specific environments. All of that said, I would point you to Claire's paper with Marla, where they did, they found these isolated quenched things at a few times 10 to the 9 and preferentially found AGN in them. So I guess there's some chance that the AGN is helping to quench the galaxy, but I don't think we could tie together the merging and the AGN activity, not with the samples that we have.
Cool, thank you. And it looks like there are not really any other questions at this point. So if that's still the case, we should just all thank Jenny again. And sorry for the technical issues in the beginning.
No, thank you. Hope to see you all in person sometime soon, and have a good rest of your day.
Thank you, you too.
Bye-bye.
Bye, everyone.